A spacetime singularity is like a big hiccup in the fabric of space and time. It's a spot where the rules of how space and time work go haywire. Scientists are trying to figure out what these weird spots mean and how they affect the universe. Sometimes it's like the very structure of space and time breaks down, which can be thought of as the end or boundary of space-time. But figuring out exactly what happens there is tough. Black holes are like cosmic vacuum cleaners. They suck in everything, even light. At the center of most black holes, there's this thing called a space-time singularity. So understanding black holes means understanding these weird spots too. But black holes themselves are puzzling. When you look at them with quantum physics in mind, the science of the very small, they start acting like hot pots, with temperature and all. This hints at a connection between big ideas like gravity, quantum physics, and heat. But we're not sure what it all means yet. Also, the way black holes change over time doesn't seem to match up with how things change according to regular quantum rules. This clash between big things like black holes and tiny things like atoms is at the center of trying to understand how gravity and quantum physics fit together. It's a big debate, and it's like trying to figure out which rules of the universe stay the same and which ones might need to change. Not many philosophers have tackled these mind-bending questions yet, so there's a lot of room for new ideas. It's like a wide, unexplored frontier, waiting for curious minds to dive in and start asking big questions. General relativity, Einstein's theory about space, time, and gravity, says that singularities can exist. But there's a big debate about what exactly these singularities are. Some people say we shouldn't think of them as specific things in space and time, but rather as problems with the whole setup of space and time itself. Imagine a rip in a piece of fabric. That's kind of what a singularity is like, but in space and time. There are two main ideas about what singularities are. The first is that a spacetime has a singularity if it contains an incomplete path, one that cannot be continued indefinitely, but draws up short, as it were, with no possibility of extension. Where is the path supposed to go after it runs into the tear? Where did it come from when it emerged from the tear? The second is that a spacetime is singular just in case there are points missing from it. Where are the spacetime points that should be where the tear is? Recently, scientists discovered a new kind of singularity called sudden singularities, which are important in understanding the whole universe. But these new discoveries also challenge what we thought we knew about singularities in general. People argue a lot about what singularities mean. Some think they show that Einstein's theory isn't perfect because it breaks down in certain situations. Others see them as exciting opportunities to learn more about space, time, and the universe. It's like we're on the edge of understanding something really big and new about how everything works. In simple terms, there's a big debate about what exactly spacetime singularities are. Imagine them as points where the usual rules of space and time don't work anymore, like a hole in a fabric. The most agreed upon idea is that these singularities happen when there are paths in space and time that suddenly stop, like a road that ends abruptly. These paths, called world lines, are like the journey of a particle or an observer through space and time. If these paths suddenly end without any way to continue, we call that spot a singularity. It's like the particle or observer hits a wall in space and time. Now, there's a complicated discussion about whether these paths should be thought of as having a proper length and how we define them. Some people argue that we should only consider the paths that are as long as they can possibly be without stopping abruptly. Others say we should think about how these paths grow and change over time. There's also talk about what these paths represent. Some say they're the paths of objects moving freely, like in outer space. But there's still a lot of disagreement about what exactly counts as a singularity and how we should define it. Scientists and philosophers are still exploring these questions, which touch on big ideas about how we understand the universe and how we think about the nature of reality. We've been talking about how to define singularities in space and time. One idea is to think of them as places where something's missing in space-time, like a hole or a tear. But figuring out exactly where these holes are is difficult. we can't just point to them like we would with a hole in a piece of cloth, because spacetime doesn't sit inside something larger that we can point to. So some people suggest looking at incomplete paths instead. These paths are like the journeys of objects or observers through space and time. If these paths suddenly stop, it might mean there's a singularity there. But even this idea has its challenges. There's a big debate about whether these missing points in spacetime can be added back in somehow. In simple cases, like a flat piece of spacetime with a hole cut out of it, it's easy to imagine filling in the missing points. But for more complicated cases, like the spacetime around a black hole, it's much harder. Some proposals try to attach new points to spacetime to fill in the gaps, but this leads to some strange problems. For example, these new points end up being too close to every other point in spacetime, which doesn't make much sense. Despite these difficulties, many physicists think it's important to find a way to define singularities more precisely. They hope that by doing so, we can better understand these weird places in the universe. But for now, there's still a lot of debate and no clear answers. When we talk about singularities in space and time, we often think about incomplete paths or weird twists in the geometry of spacetime. But there's another aspect we should consider: the curvature of spacetime. Curvature means how much spacetime is bent or twisted, like when gravity pulls things together. This curvature can get really intense near singularities, like black holes or the Big Bang. One way to understand curvature is through tidal forces, which happen when gravity pulls on one part of an object more than another. For example, when you stand, your head is farther from the center of the Earth than your feet, so it feels a practically negligible, smaller pull downward than your feet. These tidal forces can tell us a lot about how spacetime is curved. It is perhaps surprising that the state of motion of an object as it traverses an incomplete path, whether it is accelerating or spinning, can be decisive in determining its physical response to curvature pathology. Whether an object is spinning or not, for example, or accelerating slightly in the direction of motion, may determine whether the object gets crushed to zero volume along such a path, or whether it survives roughly intact all the way along it. Indeed, the effect of the observer's state of motion on his or her experience of tidal forces can be even more pronounced than this. There are examples of spacetimes in which an observer cruising along a certain kind of path would experience unbounded tidal forces and so be torn apart, while another observer, in a certain technical sense approaching the same limiting point as the first observer, accelerating and decelerating in just the proper way, would experience a perfectly well-behaved tidal force, though she would approach as near as she likes to the other fellow who is in the midst of being ripped to shreds. This complexity raises questions about how we measure things in spacetime and what counts as meaningful observations. Some types of measurements might show strange behavior, while others don't, so it's hard to say if the curvature of spacetime really tells us something about spacetime itself. However, there's one type of curvature related to a special kind of singularity called conformal singularities that we understand better. Here, the weird curvature happens in a specific part of spacetime, and we can attach a boundary to these singularities in a meaningful way. These conformal singularities are important for understanding cosmic issues like the Big Bang, and are a hot topic of research in cosmology. In 2004, scientists found out that the theory of general relativity allows for more types of singularities than previously thought. One of these is called a sudden singularity. These sudden singularities are mainly studied in models of the universe, specifically those with certain types of matter distribution. In these models, the universe's expansion is a big deal. When the universe expands, it's like blowing up a balloon. But if the expansion stops and everything starts collapsing, it's like letting the air out of the balloon, eventually leading to a big crunch. The speed of this expansion or collapse is measured by something called the Hubble parameter. A sudden singularity happens when certain parts of the expansion or the Hubble parameter suddenly changes, even though the main values stay normal. This can cause things like pressure to become infinite in a short amount of time. What's interesting is that sudden singularities don't always mean the end of everything. Unlike other types of singularities, sudden ones might not stop things like paths or curves from continuing through them. So, while some quantities may go nuts, the overall structure of the universe remains well-defined. These sudden singularities have sparked a lot of interest among physicists, but philosophers haven't really looked into them much yet. They're challenging because they're so different from what we're used to. Another weird type of singularity is called a big rip, where the universe keeps expanding faster and faster until everything falls apart, even atoms. Recent research has shown that these cosmological singularities can behave in really strange ways. Some types of big rips might trap anything slower than light but let light escape. This makes them quite puzzling and hard to understand. A black hole is a place in space where gravity is incredibly strong, pulling everything towards it. Even light, the fastest thing in the universe, can't escape its grip. This idea isn't new. Scientists have known about it since the 18th century. Imagine trying to throw a ball into the air on Earth. If you throw it fast enough, it flies away. But what if Earth was much heavier and denser? The ball would need to go much faster to escape Earth's pull. If it were dense enough, even light wouldn't be fast enough to escape, creating what's called a black hole. According to Einstein's theory of relativity, once something gets close enough to a black hole, it's like falling into a pit with no way out. No matter how fast you try to escape, you're stuck. And once something falls into a black hole, it keeps getting smaller and denser forever. The size of a black hole depends on how much stuff it has inside. For example, if you could squish all the matter in Earth down to the size of a pea, it would become a black hole. And if all the stars in our galaxy crowded together, they'd form a black hole too. The boundary around a black hole where nothing can escape is called the event horizon. Once something crosses this boundary, even light can't get out. But while it seems like time slows down near a black hole, someone falling in wouldn't notice anything unusual. It's only from far away that we see time slowing down. Thinking about black holes raises a lot of big questions. Are they really there, or just mathematical ideas? And how do we even know they exist if we can't see them directly? Scientists are still trying to figure out these mysteries, especially now that we've detected ripples in space caused by black holes colliding. One of the most remarkable features of relativistic black holes is that they are purely gravitational entities. All the standard black hole spacetime models, Schwarzschild, Reissner-Nordström, Kerr-Newman, contain no matter whatsoever. They are vacuum solutions to the Einstein field equations, which just means a solution in which the matter density is everywhere zero. Of course, one can also consider a black hole with matter present, as standard astrophysical models do for the supermassive black holes that are believed to live at the center of most galaxies, which are thought to be surrounded by strong magnetic fields and accretion disks of superheated matter. In pre-relativistic physics, we think of gravity as a force produced by the mass associated with some matter. In the context of general relativity, however, we do away with gravitational force, and instead postulate a curved space-time geometry that produces all the effects we standardly attribute to gravity. One of the most characteristic features of general relativity that sets it apart from Newtonian gravitational theory is that it admits the possibility of such curvature, gravitational effects, in the absence of matter, such as at the boundary of a black hole. Thus, a black hole is not a thing in spacetime, it is instead a feature of spacetime itself. To understand what makes a black hole, we need to look at the geometry of space and how light moves through it. Imagine space as a big grid. Light travels along this grid in straight lines, forming cones around every point. These cones show where light can go from each point in space. If something falls into a black hole, it crosses a point where these cones tilt so much that nothing can escape. This point is called the event horizon. This is a space-time diagram of a sphere of matter collapsing to form a black hole. The curvature of the spacetime is represented by the tilting of the light cones away from 45 degrees. Notice that the light cones tilt inwards more and more as one approaches the center of the black hole. The jagged line running vertically up the center of the diagram depicts the central singularity inside the black hole. As we emphasized in Section 1, this is not actually part of the spacetime, but might be thought of as the place where the structure of spacetime breaks down. Thus, one should not imagine the possibility of traveling through the singularity. This would be as nonsensical as some things leaving the diagram altogether. What makes this a black hole spacetime is the fact that it contains a region from which it is impossible to exit while traveling at or below the speed of light. This region is marked off by the events at which the outside edge of the forward light cone points straight upward. As one moves inward from these events, the light cone tilts so much that one is always forced to move inward toward the central singularity. This set of points of no return is, of course, the event horizon, and the spacetime region inside it is the black hole. In this region, one inevitably moves towards the singularity. The impossibility of avoiding the singularity is just the impossibility of preventing ourselves from moving forward in time. One interesting thing about black holes is their simplicity. Despite forming from complex matter, they can be described by just 3 numbers: mass, angular momentum, and electric charge. This simplicity extends beyond the black hole itself, affecting the space around it, making the universe simpler in a way. This simplicity raises questions about the relationship between different structures in space, which is important for understanding the nature of spacetime itself. In the traditional definition, a black hole is described by a global event horizon, which has limitations when applied to real astrophysical systems. Hayward proposed a more flexible definition based on what he calls a trapping horizon. This surface captures the idea that a black hole is where gravity is so strong that even light can't escape. Inward light rays get sucked in, and outward rays are tangent to the surface. This definition allows for local measurements to determine when someone crosses the boundary of a black hole. Ashtekar and his team introduced another approach called isolated horizons, which is more specific in terms of stress energy not crossing the horizon. They showed that this concept is related to Hayward's trapping horizon. Both of these definitions, along with traditional ones, are referred to as quasi-local black holes. There are still open questions about these definitions, like whether they match up with the traditional one in certain situations, and whether they have the same properties regarding simplicity and structure. Quasi-local black holes also exhibit an intriguing property. They seem to know about changes in distant parts of spacetime, even those they're not directly connected to. This showcases the strange and fascinating aspects of spacetime structure in general relativity. Physicists have different ideas about singularities in spacetime, especially when it comes to black holes. Some think most singularities are hidden behind black hole event horizons and won't affect us unless we enter the black hole. But if a singularity isn't hidden, it's called a naked singularity, and that can be more worrying because it's freely accessible from outside. The concern is that singularities represent a big problem for the fundamental structure of spacetime. If they're visible, they could mess up the universe, disrupting predictability and determinism. A naked singularity could be like a white hole, the opposite of a black hole, spewing out all sorts of unpredictable stuff. Roger Penrose suggested that naked singularities might not form in realistic situations, but this idea, called the cosmic censorship hypothesis, has its challenges. Some think it's hard to define and might not hold true in all cases. There's also the question of whether spacetime can be hole-free, meaning there are no obstructions preventing it from evolving normally. Some recent work by philosophers like Manchak suggests that spacetime without holes might also mean no naked singularities. Predicting what will happen in spacetime, especially around singularities and black holes, is a big challenge. Some argue that prediction is only possible when there are singularities present. This whole area of study raises questions about how physicists approach problems without clear definitions or empirical evidence to guide them. The challenge of uniting quantum theory and general relativity in a successful theory of quantum gravity has arguably been the greatest challenge facing theoretical physics for the past 80 years. One avenue that has seemed particularly promising is the attempt to apply quantum theory to black holes. This is in part because, as purely gravitational entities, black holes present an apparently simple but physically important case for the study of the quantization of gravity. Further, because the gravitational force grows without bound as one nears a standard black hole singularity, one would expect quantum gravitational effects, which should come into play at extremely high energies, to manifest themselves in the interior of black holes. In the event, studies of quantum mechanical systems in black hole spacetimes have revealed several surprises that threaten to overturn the views of space, time, and matter that general relativity and quantum field theory each on their own suggests or relies on. Since the groundbreaking work of Wheeler, Penrose, Bekenstein, Hawking, and others in the late 1960s and early 1970s, it has become increasingly clear that there are profound connections among general relativity, quantum field theory, and thermodynamics. This area of intersection has become one of the most active and fruitful in all of theoretical physics, bringing together workers from a variety of fields, such as cosmology, general relativity, quantum field theory, particle physics, fluid dynamics, condensed matter, and quantum gravity, providing bridges that now closely connect disciplines once seen as largely independent. In particular, a remarkable parallel between the laws of black holes and the laws of thermodynamics indicates that gravity and thermodynamics may be linked in a fundamental way. This linkage strongly suggests, among many things, that our fundamental ideas of entropy and the nature of the second law of thermodynamics must be reconsidered, and that the standard form of quantum evolution itself may need to be modified. While these suggestions are speculative, they nevertheless touch on deep issues in the foundations of physics. Indeed, because the central subject matter of all these diverse areas of research lies beyond the reach of current experimentation and observation, they are all speculative in a way unusual even in theoretical physics. In their investigation, therefore, physical questions of a technically sophisticated nature are inextricable from subtle philosophical considerations spanning ontology, epistemology, and methodology, again in a way unusual even in theoretical physics. Suppose one observes a quiescent black hole at a given moment, ignoring any possible quantum effects. As discussed above, there are three physical quantities of dynamical interest the black hole possesses that are, more or less, amenable to measurement, and that completely characterize the physical state of the black hole: its mass, its angular momentum, and its electric charge. These quantities, like those of systems in classical mechanics, stand in definite relation to each other as the black hole dynamically evolves, which is to say, they satisfy a set of equations characterizing their behavior. Zeroth law: the surface gravity of a stationary black hole is constant over its entire surface. First law: a change in the total mass of the black hole is determined in a fixed way by changes in its area, angular momentum, and electric charge, so that the total quantity is conserved. Second law: the area theorem: the total surface area of a black hole never decreases. Third law: no physical process can reduce the surface gravity of a black hole to zero. A black hole is stationary if, roughly speaking, it does not change over time. More precisely, it is stationary if its event horizon is generated by an asymptotically time-like killing field. On the face of it, the zeroth, first, and third laws are straightforward to understand. The second law, however, is not so obvious as it may at first glance appear. It may seem that because nothing can escape from a black hole once it has entered, black holes can only grow larger, or at least stay the same size if nothing further falls in. This assumes, however, that increased mass always yields increased surface area as opposed to some other measure of spatial extent. Surprising as it may sound, it is indeed the case that, although nothing that enters a black hole can escape, it is still possible to extract energy, that is, mass, from a spinning black hole by means of what is known as the Penrose process. It is therefore not obvious that one could not shrink a black hole by extracting enough mass energy or angular momentum from it. It also seems to be at least possible that a black hole could shrink by radiating mass energy away as gravitational radiation, or that the remnant of two colliding black holes could have a smaller surface area than the sum of the original two. It is most surprising, therefore, to learn that the second law is a deep, rigorous theorem that follows only from the fundamental mathematics of relativistic spacetimes, Hawking 1971, and does not depend in any essential way on the particulars of relativistic dynamics as encapsulated in the Einstein field equation. This is in strict opposition to the second law in classical thermodynamics, which stands as a more or less phenomenological principle derived by empirical generalization, perhaps justified in some sense by a reduction to statistical mechanics, with the temporal asymmetry of entropy non-decrease argued to hold based on the likelihood of initial states in conjunction with the forms of dynamical evolution, physically permissible for matter fields. For those who know classical thermodynamics, the formal analogy between its laws and the laws of black holes, as stated, should be obvious. One formulation of the zeroth law of thermodynamics states that a body in thermal equilibrium has constant temperature throughout. The first law is a statement of the conservation of energy. It has as a consequence that any change in the total energy of a body is compensated for and measured by changes in its associated physical quantities, such as entropy, temperature, angular momentum, and electric charge. The second law states that entropy never decreases. The third law, on one formulation, states that it is impossible to reduce the temperature of a system to zero by any physical process. Accordingly, if in the laws for black holes one takes stationary to stand for thermal equilibrium, surface gravity to stand for temperature, mass to stand for energy, and area to stand for entropy, then the formal analogy is perfect. Indeed, relativistically, mass just is energy. So at least the first law seems already to be more than just a formal analogy. Also, the fact that the state of a stationary black hole is entirely characterized by only a few parameters, completely independent of the nature and configuration of any microstructures that may underlie it, already makes it sound more than just a little thermodynamical in character. Still, although the analogy is extremely suggestive in toto, to take it seriously would require one to assign a non-zero temperature to a black hole, which at the time Bardeen, Carter, and Hawking first formulated and proved the laws in 1973, almost everyone agreed was absurd. All hot bodies emit thermal radiation. According to general relativity, however, a black hole ought to be a perfect sink for energy, mass, and radiation, insofar as it absorbs everything and emits nothing. So it seems the only temperature one might be able to assign it would be absolute zero. In the early 1970s, nonetheless, Bekenstein argued that the second law of thermodynamics requires one to assign a finite entropy to a black hole. His worry was that one could collapse any amount of highly entropic matter into a black hole, which, as we have emphasized, is an extremely simple object, leaving no trace of the original disorder associated with the high entropy of the original matter. This seems to violate the second law of thermodynamics, which asserts that the entropy of a closed system, such as the exterior of an event horizon, can never decrease. Adding mass to a black hole, however, will increase its size, which led Bekenstein to suggest that the area of a black hole is a measure of its entropy. This conjecture received support in 1971 when Hawking proved that the surface area of a black hole, like the entropy of a closed system, can never decrease. Still, essentially no one took Bekenstein's proposal seriously at first, because all black holes manifestly have temperature absolute zero, as mentioned above, if it is even meaningful to ascribe temperatures to them in the first place. Thus, it seems that the analogy between black holes and thermodynamical objects, when treated in the purely classical theory of general relativity, is merely a formal one, without real physical significance. Hawking showed that black holes aren't as dark as we once thought. Even though they suck everything in, they also give off a kind of radiation called Hawking radiation. This radiation is like heat, and it means black holes have a temperature, even though they're supposed to be super cold. This discovery links black holes with the laws of thermodynamics, which are all about how heat and energy work in regular systems. Now we see black holes follow similar rules. They have a temperature, and their size is connected to their entropy, a measure of disorder. It's like they're part of the same family as hot objects. Physicists argue that this link between black holes and thermodynamics isn't just a coincidence. They say black holes are really like thermodynamic systems, following the same laws but in a different way. Others are more skeptical, saying there are still big questions about whether these connections are real. But the idea that black holes are like hot things has opened up a whole new area of study, raising questions that physicists are still trying to answer. So, where does black hole entropy come from? In regular thermodynamics, entropy measures how much we don't know about a system. For example, when we talk about the entropy of a gas cloud, we're saying we don't know exactly where each molecule is. We just talk about general things like pressure and temperature. Trying to apply this idea to black holes is tough because our usual tools for describing systems don't work well with them. We need a new way to think about what's happening inside a black hole. One idea is that there are tiny building blocks inside a black hole, maybe something to do with strings or loops. These building blocks could have different arrangements or microstates, and the number of these microstates might be related to the entropy of the black hole. Some theories suggest they have to do with the geometry of the event horizon, the point of no return around a black hole. Others say they might be connected to the basic structure of space itself. Whatever the case, understanding black hole entropy could change how we think about fundamental concepts like heat and energy. It's a puzzle that's pushing us to rethink some big ideas in physics. If a black hole emits radiation according to Hawking's theory, it appears to lose mass, which seems to break the classical second law of black hole mechanics. Similarly, if we dump matter with a lot of disorder, high entropy, into a black hole, we might break the ordinary second law of thermodynamics, because the outside of the black hole, which is cut off from the rest of the universe, decreases in disorder spontaneously. But when we feed matter to a black hole, its event horizon, the point of no return, gets bigger. On the flip side, if the event horizon shrinks due to Hawking radiation, the disorder outside increases. To make sense of these scenarios, physicists proposed a combined law called the Generalized second law. It basically says that the total of a black hole's size and the disorder of everything outside it can't decrease over time. This idea brings up lots of questions about how it affects our understanding of thermodynamics and the physics of black holes. The ordinary second law of thermodynamics is a rule we've established based on how things usually behave in the world around us. It's like saying hot things cool down and messy things get messier over time. But when we talk about the generalized second law, it's a bit different. It's like a fancier version of the ordinary second law, with more math and rigorous proofs to back it up. What's interesting is that there isn't just one way to prove this generalized second law. There are actually many different ways, each with its own set of assumptions and math tricks. Some proofs are more complicated, some are simpler, and they often apply to different situations, like classical physics or quantum mechanics. When scientists try to prove this law, they have to make decisions about things like which parts of a black hole to focus on, which mathematical formulas to use, and what assumptions to make about how things work. And because there are so many different ways to prove it, it's not always clear if they're all saying the same thing. In fact, some of these proofs might even contradict each other because they're based on different ideas or assumptions. So, while the generalized second law sounds like a simple idea, proving it turns out to be quite complex and involves a lot of careful thinking and decision-making. When Bekenstein suggested that black holes have entropy proportional to their area, it raised some big challenges. Jarok proposed a scenario showing that if a black hole has a temperature at all, it should be absolute zero. This scenario seemed to lead to problems with a law called the generalized second law. Far away from a black hole, prepare an essentially massless box to be full of energetic radiation with a high entropy. Then the mass of the radiation will be attracted by the black hole's gravitational force. One can use this weight to drive an engine to produce energy, to produce friction from the raising of a counterweight, while slowly lowering the box towards the event horizon of the black hole. This process extracts energy, but not entropy, from the radiation in the box. One can then arrange for all the mass energy of the radiation to have been exhausted when the box reaches the event horizon. If one then opens the box to let the radiation fall into the black hole, the size of the event horizon will not increase because the mass energy of the black hole does not increase, but the thermodynamic entropy outside the black hole has decreased. Thus, we seem to have violated the generalized second law. Scientists have suggested different ways to deal with this problem, like setting limits on entropy or considering how the object being lowered into the black hole interacts with the radiation around it. But none of these ideas fully solve the problem. This issue brings up some deep questions about physics. The ordinary second law itself is debated by scientists and philosophers, so it's natural to wonder if it should apply to black holes. However, the connection between black holes and thermodynamics is too important to ignore. In fact, the generalized second law is the only known law that ties together general relativity, quantum mechanics, and thermodynamics, making it a key to understanding the most basic aspects of the universe. In response to a problem with the generalized second law pointed out by Garroch, Bekenstein suggested a limit on how much entropy a certain space region can have. He proposed that this limit is set by the entropy of a black hole with a horizon encompassing that region. Bekenstein thought that a theory called quantum gravity, which is believed to be hinted at by black hole thermodynamics, might enforce this limit. Another reason to think there's a limit on entropy comes from imagining a region with more entropy than a black hole of the same size. If we squeeze all that entropy into a black hole, it couldn't be bigger than the original region. But this would break the generalized second law. So it seems there's a fundamental limit on how much entropy a region can hold. Based on these ideas, Gerard 't Hooft suggested the holographic principle, saying the number of fundamental ways something can be in any region is linked to the black hole's entropy. This principle is interesting because it implies that the number of ways something can be increases with the area surrounding the region, not the volume inside it. This goes against what we usually think about how systems work. However, there are doubts about whether these ideas are true. Some scientists have suggested other ways to save the generalized second law without needing this limit on entropy. This ongoing debate has connections to philosophical questions about space and time, like whether space has more than 3 dimensions and whether space is something real or just a relationship between objects. The ordinary second law of thermodynamics has big philosophical implications, but it's not typically used to prove other important ideas in physics. On the other hand, the generalized second law is different. It's been shown that it can prove some really interesting things. For example, it rules out things like wormholes, which would allow faster-than-light travel, negative masses, and time loops. It also suggests that certain baby universes, which could lead to a multiverse, might not be possible. The generalized second law also has positive outcomes. It implies that space-time inside black holes and in the past of certain cosmological models will always have holes, even when you consider quantum effects. This goes against the hope that quantum physics would smooth out these holes. It helps derive energy conditions in general relativity, which are important for understanding singularities and black holes. This is remarkable because these conditions have been assumed but not proven until recently. Finally, a version of the generalized second law suggests that in certain situations, even when energy conditions are violated, geodesics, the paths that objects follow through spacetime, will still focus and converge. This is significant because it challenges some assumptions about how singularities work in spacetime. The idea that black holes have entropy suggests that gravity itself might have entropy, as proposed by Penrose. This is because gravity tends to make matter come together, which makes things less orderly over time. Since the late 1970s, researchers have found ways to attribute entropy and temperature to different types of boundaries in space, not just black hole horizons. Some even think that cosmological events like the Big Bang could have their own entropy. This has led to proposals for measuring gravitational entropy more generally. These discoveries raise big questions about entropy as a concept. How can something usually linked to materials be connected to empty space? How does gravitational entropy relate to the regular entropy we're familiar with? And does this shed new light on philosophical questions about how different scientific theories connect with each other? In light of the notorious difficulty of constructing a theory that incorporates and marries quantum mechanics and general relativity, a theory of quantum gravity, it may come as a surprise to learn that there is a consistent, rigorous theory of quantum fields posed on the background of a classical relativistic spacetime. Quantum field theory on curved spacetime, however, differs from standard quantum field theory in one profound respect, that difference ramifying into every part of the theory. A generic relativistic spacetime has no group of symmetries comparable to the Poincare group for special relativity. There is correspondingly no distinguished vacuum state and no natural notion of a particle. This means, for instance, that one cannot employ many familiar and useful techniques from standard quantum field theory, and one must take care in the use of most of the others. One expects that such a framework would find its most natural application in the treatment of problems in which, in some sense or other, the curvature of spacetime is well above the Planck length, insofar as there are some theoretical grounds for suspecting that in this regime, one can safely ignore any quantum properties of the spacetime geometry itself. In this vein, its most popular and successful applications have been to problems involving particle creation in the early universe and in the vicinity of black holes. Now, according to general relativity, a black hole ought to be a perfect sink for energy, mass, and radiation, insofar as it absorbs everything and emits nothing. It was therefore more than shocking when Hawking, 1974-1975, predicted that, when quantum effects are taken into account, a black hole ought to behave rather like a perfect black body, in the sense of ordinary statistical thermodynamics. A stationary black hole should emit thermal radiation with the Planckian power spectrum characteristic of a perfect black body at a fixed temperature. It glows like a lump of smoldering coal, even though light should not be able to escape from it. As with the generalized second law, one of the most fascinating aspects of Hawking radiation, from a foundational point of view, is the multiplicity and multifariousness of the derivations known for it. They also differ radically among themselves with regard to the mathematical rigor of the framework they adopt and the mathematical character of the structures they assume. And almost all are valid in different regimes than the others, using different types of physical systems and different approximations and idealizations, basing their arguments on different physical principles with varying degrees of physical perspicuity and intuitiveness. In consequence, these different derivations seem to suggest different physical interpretations of Hawking radiation itself, both for its origin and for its character. It is thus not even clear, at a foundational level, what the physical content of the prediction of Hawking radiation is. Indeed, as in the case of the generalized second law, some of the derivations of Hawking radiation make assumptions that seem to contradict some of the assumptions of other derivations. But if A implies B and not A implies B, then B must be a tautology. Since this is an unappealing attitude to take towards Hawking radiation, some other way must be found to reconcile the contrary derivations. Because the interpretation of quantum field theory itself, even in the flat spacetime of special relativity, is already so contested, fraught with problems, and just poorly understood in general, one may think that there's even less of a chance here to get a grip on such issues. Contrarily, one may also think that the very fact that the phenomena are so different here than in ordinary quantum field theory may suggest or afford us new avenues of approach to the traditional problems that have so long frustrated us. The existence of Hawking radiation has a remarkable consequence, as Hawking, 1976, pointed out and Unruh, 1976, elaborated. The fact that a black hole radiates implies that it loses mass energy, and so will shrink in seeming violation of the area theorem. Because there is no limit to this process except that imposed by the total initial mass of the black hole itself, eventually the black hole will radiate itself entirely away. It evaporates. This prediction clearly bears on the issue of cosmic censorship. If the end state of the evaporation leaves the previously hidden singularity open for the rest of the universe to see, all the potential problems. There is, however, a seemingly even deeper problem posed by the possibility of black hole evaporation, one that raises doubts about the possibility of describing black holes using any standard formulation of quantum theory. According to standard quantum theory, the entropy of a closed system never changes. This is captured formally by the nature of the evolution of a quantum system, by the technical property of unitarity. Unitary evolution guarantees that the initial conditions, together with the Schrödinger equation, will fix the future state of the system. Likewise, a reverse application of the Schrödinger equation will take us from the later state back to the original initial state. It is usual to characterize this feature by the claim that quantum evolution preserves information. If one begins with a system in a precisely known quantum state, then quantum theory guarantees that the details about that system will evolve in such a way that one can infer the precise state of the system at some later time, and vice versa. This quantum preservation of details implies that if we burn a chair, for example, it would in principle be possible to perform a complete set of measurements on all the outgoing radiation, the smoke, and the ashes, and reconstruct exactly what the chair looked like. If we were instead to throw the chair into a black hole, however, then orthodoxy holds that as a consequence of the no-hair theorems, it would be physically impossible for the details about the chair ever to escape to the outside universe. This might not be a problem if the black hole continued to exist for all time, since one could then assume the information encoded in the chair still existed behind the event horizon, preserved by the unitary evolution in that region. The existence of Hawking radiation, however, tells us that the black hole is giving off energy, and thus it will shrink down and presumably will eventually disappear altogether, along with whatever stuff had fallen past the event horizon before that. At that point, the details about the chair will be irrevocably lost. Thus, such evolution cannot be described by the standard laws of quantum theory. This is the information loss paradox of quantum black holes. Although the paradox is usually formulated in terms of information, the issues is often put here as being the maintenance of correlations between different systems, as this is a physically more perspicuous notion that lies at the bottom of the paradox and is much less problematic than the notoriously vexed and nebulous concept of information. The attitude that individual physicists adopt towards this problem is strongly influenced by their intuitions about which theory, general relativity or quantum theory, will have to be modified to achieve a consistent theory of quantum gravity. Spacetime physicists tend to view non-standard quantum evolution as a fairly natural consequence of singular spacetimes. One would not expect all the details of systems at earlier times to be available at later times if they were lost in a singularity. Hawking, 1976, for example, argued that the paradox shows that the full theory of quantum gravity will be a theory that does not obey the standard dynamical principles of quantum theory, and he began working to develop such a theory very soon after first promulgating the paradox. Unruh and Wald, 2017, develop an extended review and defense of this position. Particle physicists, however, tend to view black holes as being just another state of a quantum field. If two particles were to collide at extremely high energies, they would form a very small black hole. This tiny black hole would have a very high Hawking temperature, and thus it would very quickly give off many high-energy particles and disappear. Such a process would look very much like a standard high-energy scattering experiment. Two particles collide, and their mass energy is then converted into showers of outgoing particles. The fact that all known scattering processes obey the standard dynamical principles of quantum theory, and above all unitarity then, seems to give us some reason to expect that black hole formation and evaporation should also do so. In particular, today there are four main ways of trying to address the problem that have a fair amount of support in different segments of the physics community. Acceptance of the loss of unitarity, the first response. Black hole complementarity, an instance of the fourth kind of response. Firewalls, an instance of the fifth. Hawking radiation's deviation from perfect thermality, an instance of the third. The problem arises when considering what happens to the information of matter and energy that falls into a black hole. According to the principles of quantum mechanics, information should not be lost in any physical process. It should always be conserved. This principle is known as unitarity. However, Hawking radiation appears to be thermal in nature, meaning it carries no information about the matter that formed the black hole. This leads to a conflict known as the information paradox. If information is lost when matter falls into a black hole and is subsequently emitted through Hawking radiation, it violates the principle of unitarity. One proposed resolution to this paradox is to accept the loss of unitarity in certain scenarios involving black holes. This viewpoint suggests that while unitarity is a fundamental principle of quantum mechanics, it may not necessarily hold in all contexts, particularly in extreme gravitational environments, such as those near black holes. By accepting the loss of unitarity, physicists explore the implications for the fundamental laws of physics and attempt to reconcile the apparent conflict between quantum mechanics and general relativity in the context of black hole physics. This approach is one of several competing ideas aimed at understanding the fundamental nature of black holes and their behavior within the framework of modern theoretical physics. Black hole complementarity is a concept proposed by theoretical physicist Leonard Susskind, along with Gerard Hooft and others, to address the apparent contradictions between quantum mechanics and general relativity in the context of black holes. It suggests that seemingly contradictory descriptions of black hole physics can coexist and remain consistent depending on the perspective of different observers. The core idea of black hole complementarity stems from the fact that different observers in different reference frames experience different aspects of the physics near a black hole. In particular, observers outside the black hole, known as external observers, and observers falling into the black hole, known as infalling observers, have fundamentally different experiences due to the effects of gravitational time dilation and the curvature of spacetime near the event horizon. External observers who remain outside the black hole perceive the process of matter falling into the black hole as undergoing gravitational collapse and eventually crossing the event horizon. In contrast, infalling observers experience a different scenario. For them, crossing the event horizon does not necessarily entail encountering a dramatic physical boundary or encountering extreme conditions, such as the proposed firewall, but rather they experience a smooth passage through the horizon. When black holes evaporate, it creates some big problems for our understanding of how tiny particles work. Imagine a huge star collapses into a black hole. After the black hole evaporates, it's likely that it won't have any particles left from the star. This breaks a rule we thought was always true about the conservation of certain types of particles. Now, scientists are more worried about this rule breaking than they are about other weird things in physics, like how particles behave when we're not looking at them. A problem called the measurement problem. Well, one reason might be that most scientists who think about these problems don't actually do experiments, so they don't think about the measurement problem much. Also, some scientists work on big questions about the whole universe, where these rule-breaking problems don't come up as much. But there's another puzzle related to black holes called the page-time paradox. It's about a special time in a black hole's life when half of its original messiness has disappeared. This paradox shows a big inconsistency between how we usually think about black holes and how we think about them when we use certain rules from statistics. This puzzle is a big deal on its own and doesn't have much to do with the rule breaking we talked about earlier.